moving on from part one, moving out to dealing with how multiple planes interact. Right, the intersection of two planes is a line, and we can kind of think about this. I'm going to try to draw this as best as I can, but if I've got one plane right here, so we'll call this pi 1, and if I've got another plane kind of sticking up this way, cutting through like this, I'll call it pi 2. Right, you can kind of imagine that their intersection is kind of between these points here. And this would be my intersection. It's a little tricky to kind of figure out this intersection or figure out how planes are parallel because we don't really have information to go off of right away. However, one thing we can look at is their normal vectors. So two planes are parallel if their normal vectors, which with planes you might see this used interchangeably with direction vectors. But if they are also parallel or collinear, then their planes are also parallel. And this just comes from this plane extends out infinitely, right? I can't point this to a specific direction that this is going in. I can, however, point to, say, a specific vector, a specific direction. This might be pointing perpendicular to the plane, right? And here is my normal vector in blue over there. So if I kind of imagine a second plane below it that is parallel to it, call this, I guess, pi 3 now, keeping track. And I find this other normal vector right here. Right, we can see that these two normal vectors in blue are collinear with each other, right? So n1 and n3 are parallel, which means that their planes are also parallel. The next question, of course, is where do I find these? All I'm going to do is take my coefficients from each term of the Cartesian equation. Right, so in general, my normal vector is going to have the form a, b, c coming right out of the plane equation being ax plus by plus cz equals d. So, given these three planes here in our next example, let's show that first that pi 2 and pi 3 are parallel to each other. And just as I said, in order to do that, we want to find direction vectors or normal vectors. So my normal vector for plane 2 is just the coefficients. So my coefficients are 1, 2, and -1. And likewise for pi 3, my normal vector is 2, 4, -2. And we can see that they are proportional to one another, right? We can see that I can actually express n3 as twice n2. And because I can do that, right, one is kind of a scaled version of the other, that tells us right off the bat that these two planes are parallel. Great, moving on. So now let's show that our other pair of planes, right, plane 1 and plane 2, intersect, and let's find the equation of that intersection. Well, just as anything else, anytime I want to find this intersection or anytime I want to kind of deal with these two, what we would normally call simultaneous equations, right? I'm dealing with two equations at the same time. I'm going to create a system. So 2x minus 3y plus 5z equals 0, and x plus 2y minus z equals 0. I have fewer equations than I do variables. So this is going to mean that one of these variables is what we're going to call a free variable, meaning that essentially its value is not really relevant to the outcome of the problem, and I'll show you how to deal with that in a second. Let's see, I think it may be easiest to work this, I guess we'll do it by elimination. Let's multiply this second equation by 5. So I get my first equation, and then just kind of underneath it, I'll just write this scaled version here. Oh, sorry, this top equation should be equal to 1, my bad. going a little too quick, equals 0. And if I combine these, I'm going to get 7x plus 7y equals 1. And in the interest of trying to solve these, let's see what I can do here. I'm actually going to keep an eye on the second equation, because part of the reason I got stuck earlier is that I could have also done this by substitution and written z as x plus 2y, and that actually might be a little helpful later on, because this now gives me a solution for z, sort of. I wonder if I can do that also over here with y. If I rearrange some things for y, looks like if I subtract the 7x and then divide by 7, right, I'm going to get 1/7 minus x. All right, and it looks like I'm getting somewhere, right? I've got a rule for y and a rule for z, so I wonder if there's a way to eliminate the y from z. So let's see, if I just kind of substitute it up here, we're going to get z equals x plus 2 times 1/7 minus x. So 2/7 minus 2x, z equals 2/7 minus x. And it appears normally that we would be stuck here, right? I've got two solutions. I've got a kind of a rule for y and a rule for z, but I have no way to find x itself, and that's okay, because like I said, I have more variables than I do equations, which means one of these has to be a free variable. So the way that we're going to write this solution is that, let's see, x is kind of just a free variable, y is 1/7 minus x, and z is 2/7 minus x. And normally we don't like to write it this way, right? We still want to assign x something. So we're going to give it a placeholder, and we're just going to call it, say, k. And since x is k, that means these x's are also k, and k is a real number. Well, now this starts to look like my parametric equation of a line, right? This is my intersection. Here, I'm going to call it L1. Right, this looks like it's in parametric form, which is great. And if I wanted to go a little farther and write my final answer in Cartesian form, we know that we can just eliminate k. So I'm going to get x equals 1/7 minus y equals 2/7 minus z. And if you prefer not to have the fractions, of course, and we can kind of juggle things around, right? I might want to write this even as, I think it would be valid if I did 1 minus 7y and 2 minus 7z, which will help me later on if I wanted to find, say, a direction vector of this line. So again, a lot of what we're doing is not new. We've actually been kind of dancing around this term linear algebra for quite some time without actually addressing it by name. All linear algebra is really working in this kind of space with matrices, with systems, and kind of solving this way.